Hi everyone and welcome back to a new video about system identification. This is our example number 7. In this example I will discuss the response for a pure differentiator. And again we will look at our calculations and simulations in Matlab to verify our calculations. So let's look at our example. In this example we have a different type of input, and the response is not a step response but the ramp response. So the system has a ramp response, and that means the input is a ramp, and ramp is actually a linear increasing signal. In this case the input R is a ramp with a slope of 6/20. You can already see that from this point. So it is 6 height at 20 seconds, or you can have also 0.3 as the slope. So that's actually the slope of our ramp. And we would like to determine the transfer function using this plot. And what you see is the blue line is our response, and in this case it is a step output signal. So it is actually the reverse of what we did in the previous example, example number 6. We had a step input that was actually the red line, and the curve at the response was the blue line that was actually increasing response. So this is actually the reverse one. And what you see here is that the signal is also a constant for a ramp input. So what does that actually mean? We will see that shortly. So let's look at the solutions and we will go through that step by step. So let's look at our solutions, and of course we'll make some observations from the plot, and that will lead to our the transfer function step by step. So let's also look at the output in more detail. What you see is, as said before, it's a step signal, and that is the result of a ramp input. Now, what does that actually mean? If you have a ramp input and that results in a step, that means that you have a differentiator. So you have differentiated actually a linear function which is going up, and that differentiation will result in a constant value, which is actually just the slope of this line, and that is actually then a pure differentiator. So you will actually have a differentiator action if your input is a linear increasing function that will always have a constant if you have a pure integrator. What you also see is the amplitude of this step signal, and the output is 8. So that will be also used later on for our transfer function of the system. So what is actually the transfer function model for this pure integrator? So we know that it's a pure integrator. So how can we do that? Before we move on to this one, let's make another note. In this case, why can't we use a step input for this pure integrator? Now, if you do a step input, so consider that this blue line was the input, then if I want to determine or already calculate what the response for that one is, since this slope is infinite, and by differentiating that one means actually that you have an infinite slope. So that is actually not the best signal to measure or to check that this is a differentiator. So if you have a slope which is linearly increasing, that will give you a more accurate result and also can be determined easily. So that's one of the reasons why we use a ramp input for our differentiator. So getting back to the transfer function model of the pure differentiator. Pure differentiator, we only have, you will see that shortly, 1 0 at the origin, and no pole and no delays. That's actually the pure differentiator. So the transfer function is shown here. We have a k sub d, which is then the one of the parameter, and also the tau d, and of course the s. And you can see already here that the 0 is at the origin, because if you make the s equal to 0, this will be a 0. So the kd is the differentiator gain. So that is at some particular time t1. I already said that also in the previous example. And the tau d, which is a differentiator time constant, that is at also this particular time exact same as that we did for the kd. So we will do that shortly, and you will see how we can determine that. Now the transfer function specifically for this system can be then determined using step-by-step procedure. Look at the kd first. What is the kd? Also at particular time, of course. In this case, we already know that this is 20 so we can use that as our measurement point. So let's do that for t1 at 20 seconds. You can see that then the response at that value, so the response was blue line, and at 20 seconds it is also 8, so it is 8 for this one, and the input, that is the red line, is at 20 seconds it has a value of 6, so it is 8/6 for this KD, or simplified 4/3. That is our differentiator gain at this time of 20 seconds. For the time constant, again at the same time, that will be just that 20 seconds, so you will combine these, and the product of these two, which is of course interesting here in our transfer function, will not change. That is actually what we all discussed in the pure integrator example number 6. That ratio was Ki over tau I was not changing, so it will stay constant no matter what the time you take in the plot. This is also valid here, it's also true here. No matter what your time is here, you can also take 10 seconds or 5 seconds or 25 seconds. You will get exactly the same product, Kd times tau d, which is then here 4/3 times 20, that will give you 80/3. That is actually what you have here for your product. So alternatively, if you say this is a little bit confusing or a little bit lengthy calculation, you can also say the following. Alternatively, for this response type, so for this system, you can say this product, which is of course interesting for us, not the specific values, you can say the output amplitude, so the amplitude of your output signal divided by the slope of your input. That is of course 8/0.3, and that is all the same, so you will get 80/3, which is of course much faster than this one. Why did I do this? You can now follow that step by step, and you can also get your response and the transfer function in a different form. So that's actually why I did that. So this is an alternative form that you can use for your analysis. Then we have the following transfer function. Again, we know already the product, and I just substitute it in this model. I will get 80/3 times S. That's actually what we have now here. If you say, I want to do it in a little bit different form, there is an alternative calculation which uses the Laplace transform directly. The steps are the following. You determine the Laplace transform for the input, which is this line R, and then you will determine the Laplace transform for that one. You will also determine the Laplace transform of your output signal, so which is the Y, in this case the blue line, and then you will calculate the ratio, which is then the transfer function H. That is also possible. So for that, of course, we need the time representation of this input and also the output. So the time representation for the input is 0.3 t, which is just this linear increasing line, and it starts at its origin, so that's actually only this. And for the output blue line, it is 8 times the step signal. Why? Because it has an amplitude of 8, and this is a step signal, so that's why we have a step u, which is the mathematical expression for the step, and it has an amplitude of 8. Now if you now get the Laplace transform for the input, you can look in the table that the t only will give you 1/s squared. Now of course you have a 0.3 here, that will be your amplitude in the numerator, so that's actually 0.3/s squared. The Laplace transform for the output in a similar form, the ut only in the Laplace transform table, that will give you 1/s, and you have now the amplitude that will give you 8 times that 1/s, or 8/s. If you combine these using this expression for the transfer function H, then you will have this, and if you substitute the values for the output and input transfer function, you will have this expression. Simplifying this, you will get exactly the same as we have here, which is 80/3s. That is now the transfer function of this pure differentiator. So let's check this, what we have in our simulation. So transient response, in this case ramp response. This is the ramp response. What you see is this line, blue line, is our input, and this orange line is our response. So I have the Y, which is then the response, and the R, which is then our input. You can see here in this plot, and this is the transfer function again, at 20 seconds it was 6, so that is correct. And I can also see at, for example, that my output at 10 is 8 and my input is at that 10 3. So you can already see that this is a linear function, because if I decrease the time by a factor of 2, the amplitude also decreases by a factor of 2. That is actually a linear action. So you can see that this is for sure for this case clear, and you can also see that this output will stay for all values of the time at 8. So that is correct, and that will mean that this transfer function, just looking at the ramp response, is the correct one. But let's also look at the Bode plot. That is the frequency response. So that is the Bode diagram. Now what you see here, again, this is our transfer function. I can see already the interesting point, which is then the magnitude is approximately 0 dB, because I wasn't able to get it exactly at 0 dB. That is at this frequency, and this will be now checked because this frequency is interesting. We already discussed it in the previous example that this frequency is also called the unity gain frequency. Why? Because the magnitude here is approximately 0 dB. Of course, this must be exactly 0 dB. And 0 dB means in scalar form 1. That means you have a amplification or a gain of 1, that is unity gain, and that means at that frequency 0.0375 radians per second you have a gain of 1 or 0 dB. That's interesting. Now at that frequency you have also a phase which is 90 degrees, but the interesting thing is that phase will stay plus 90 degrees for all frequencies. That's actually the characteristic of a pure differentiator. It has always a phase shift of plus 90 degrees. You can also see that from the expression in the j omega domain that will be given also shortly here. What you also see is to give you another check that this is 0 dB and it has a frequency of 0.0375, but if you increase the frequency by 1 decade, so you will multiply this by 10, you will go to 0.375, then the gain of that line, value of that line will be 20. So actually I will increase by 20 dB. So that is also a characteristic of a pure differentiator, which is actually a first order high pass filter. You can also designate like that. So you can see the gain goes up by 20 dB if you increase your frequency by 1 decade. Of course, if you increase it again by 1 decade, you will get to 40 dB. That's actually the characteristics of this plot. Now at same frequency here, you will exactly have again 90 degrees for the phase shift. That will not change, so that's actually the same. So let's look at this frequency in more detail. If I just change my S in j omega, so I go from the S domain to the j omega domain, I have this, so only changing the S in the j omega, and then I can use this standard formula, which then has a tau, which is specifically the differentiator time constant, specifically in this model. Then this tau time constant is then just the value here, which you actually see here. So if you just place it here at the back, you will have 80/3 seconds. That is actually my time constant. Now we know that this has a relationship with the unity gain frequency, which is then the omega sub t, which is the transit time or the unity gain frequency, is 1 over that value. So 1 over that tau, and that is 3/80. And if you do the math here, just punch it in your calculator, you will get 0.0375 radians per second, exactly what we see here. That is actually the reason why we have this frequency for that value. Now we will of course check that this is indeed 0 dB or 1 also. So let's do that also in the step-by-step form here. Now just substitute this value for 3/80 in this expression for the h for transfer function. So what do I have? I just substitute it in here. I have 80/3 times j 3/80. Now this will cancel each other out. It will just do 1. So I will only have j as an expression for my transfer function at this frequency 3/80. So if I want to calculate the magnitude of that one, that is just 1 or 0 dB, and we already have that also in our label here. So at this frequency, which is 3/80, I have a gain of exactly 0 dB actually here, and this is then also calculated, proven here. And that is again a proof or confirmation that this system is, the transfer function of this system is correct. That is actually what we have seen in this simulation results. We will also do that in the simulation in Matlab in real time, so let's jump to Matlab. So this is the Matlab simulation for this example number 7. I have already prepared the system identification example number 7. Again, defined a Laplace parameter. This is our parameter for our system: differentiator gain, differentiator time constant, kd, and also the tau d. We have discussed this. It is 4/3 for the kd and the tau of 20 seconds. And this was a transfer function model. What I also have is, since I will use the command, the step in the Matlab, I need to make the input already a step expression in the Laplace domain. That will be clear shortly. So I will have a 0.3 over s, that is already an integrator, and that will be again put in the step response command. That will be then an increasing line in our plot. It will be given shortly. And the output y is of course then r times that transfer function h, and that will be the response, and we will plot them both to see what's going on. So let's run this and see what's going on. So I'll run this. I have it in the command window here on the left, and let's check the h to make sure that this is correct. And this is AD/3. You can check that. So it is AD/3. So approximately that one. So this is the AD/3s. So that's actually correct. Now we can now move on to our step, and then after that to the body plot. So let's do step h, or I mean y of course, and then also the r, because we will also need to have that one. And then in grid on, you can see then that we have both curves in one plot. So we will have the response. This is of course a ramp response, so it is not a step response. So let me change that. Of course we will do step, but of course what we generate is a ramp response. So that makes sure that this is not a step response. Let me change this. So this is the ramp response. Okay, this is a ramp response. The blue line, I mean the orange line, is in this case the input, and the blue line is in this case the output. So what we had was 20. That was at 6, so I can go to 6 and make this larger. You can see this is indeed 6. And if I go, for example, to 10, which is then value in time 2 times smaller, then I have an amplitude of 3. You can also see that the output here is a constant at 8. So it is always 8. It will not change if the time is changing. You can also give it labels here. So let me get also the label and make this larger, so you can see that this is indeed y, which is the output, and r, which is the input. You can see that this is indeed increasing linearly, and it has a slope of 0.3, because at 10 seconds I have an amplitude of 3. And that is actually the confirmation that this is indeed the correct system, just looking at the ramp response. So let's also look at the body diagram, or the body plot. So that is the frequency response. So I will move the body, and in that case I am only interested in h, because that is only the system and not in the input itself, because that h is just a ratio. Okay, do also the grid on. Of course it must be grid on, because okay, that error is not really interesting. Let me make it the grid on here. So that is the full screen. And then let me make it a little bit smaller, that you also see the rest of the picture. Maybe let's make it completely. And you can see here, if I now go with the frequency, such as you can see also the unity gain frequency in this analysis. Let me change the limit or the x-axis. So I will go to 0.01 and all the way to, you can see if I want to go to the 0 dB, which is at this, you can see it's approximately 0 dB, approximately, and then I have the unity gain frequency as we have discussed. Now if I now go up by 20 dB, all the way up, 20 dB, then this is the 1 decade increase in the frequency, and you can see that this is increased by 20 dB. That's actually the proof that this is indeed a first order high pass filter, which is a pure differentiator. But you also see that the phase is always 90 degrees. It doesn't matter what you do. Let me make it larger. So it is always 90 degrees. So at all frequencies, doesn't matter which frequency you have. So unity gain frequency you can check. We have checked the slope in the magnitude, and the phase is always 90 degrees. And that's a confirmation in the frequency response on the Bode diagram that this system transfer function is correct. So that was this example of a pure differentiator. So we have done the pure integrator in the previous example. This is the pure differentiator, and we have also seen in previous examples different responses for the first order and the second order systems. So we will of course continue with different examples to clarify this situation even more, but we have also some delays or maybe some shifting in the vertical axis. So that will be all worked out here step by step using different examples. If you have questions, comments, please let me know. I will try to answer them as soon as possible. Thanks, and I hope we will see each other again, and see you next time, and take care.